This is going to be the content: conductors, semiconductors, and insulators. I hope that maybe we can reach up to the p-n junction by the end of this lesson. So the first thing we look at is the electronics. Of course, this is about free electrons, and it finds an application in so many appliances right now, even in our current classes. Like we use calculators in class, we have clocks, we have musical instruments, computers, robots, all those they find the application in electronics, where we have transistors, we have semiconductors, we have diodes, and many others. Now we classify materials in terms of electrical properties into conductors, insulators, and semiconductors. For the conductors, they have free electrons. These ones are not tightly bound to the nucleus of the atom. They can move. Like when we talk about a material being a good conductor, it means it has free electrons that are free to move to allow for conductivity or the flow of electrons. We also have those that have fixed electrons. They cannot move. They are fixed, and those are insulators. Like wood is an insulator. We have rubber is an insulator. Then we have those ones that are in between the conductor and the insulators. They have some conducting properties depending on the condition or the circumstances. We shall look at the circumstances under which a semiconductor will conduct. They are in between the conductors and insulators. For example, we have silicon and we have germanium. Then we have, when you bring two atoms together, what happens is that energy levels will split into smaller levels, which we call bands. You have done energy levels in chemistry, where we have the outermost shell, where we have electrons moving there. So when you bring these atoms together, we will create, or we will have the energy level splitting into other smaller ones. We have their energy shells. They are known as, we have the K, we have the L, and we also have the M, and many others into smaller bands. We call them bands. And that is because of the interaction of the electrons in terms of electric and magnetic fields. Now we have three different types of bands. I've said it will split into three energy bands. Smaller bands energy levels we call bands. We have a conduction band, we have a valence band, and we have a forbidden band. For the conduction band, the electrons are free to move under the influence of an electric current. That means we have free electrons that will be moving in the conduction band. And that classifies where conductors are. They would have most of the electrons or their electrons in the conduction band, where now the electrons are free to move. Then we have valence band, where electrons are not free to move. They don't move at all. Very few. If at all it is unfilled, they will now move from one gap to another one, but they don't move within the valence band. Then we have the one in between the conduction and the valence band. And you can see that the one that I'm talking about is this one. Okay, this one is for conductors. Between the conduction band and the valence band, we have what we call the forbidden band. It is also known as forbidden energy band. Remember, all these are energy levels. So the electrons will have a certain amount of energy. This is an energy gap between the conduction and the valence band. And of course, its width will determine whether it will be a conductor or a non-conductor. Looking at the conductors, these ones, they have free electrons. Looking at the conduction band, here we have free electrons. For the valence band, we have very few electrons and they are not filled. This one does not have a forbidden band. You can see the conduction band and the valence band, this is supposed to be valence, not variance. It's valence band, they overlap and it does not have a forbidden gap. It doesn't have any forbidden band since the two of them are overlapping. When you increase the temperature of a conductor, we said in Form 3, the resistance increases. Now, why does the resistance increase? Because these atoms will now start vibrating at a higher level and they will interfere with the electron flow. And remember, the resistance is to the electron flow. So when you increase the temperature, you increase the vibration of the atoms, and therefore interfere with the electron flow, increasing the resistance. So an increase in temperature will cause an increase in the resistance of that conductor. We have insulators. For the insulators, you can see we have an empty conduction band. It has no electrons. There are no electrons here, and that is why it will not conduct an electric current. So we have an empty conduction band. We have an energy gap. This is a forbidden gap. Then we have the valence band is completely filled. Note, it is not variance, it is valence, V-A-L-E-N-C-E. The valence band is completely filled with electrons. And remember, we said there is no movement of electrons within the valence band. So even if they are here, they cannot move, and therefore does not conduct. Then the forbidden band has it's an energy gap. Remember, all these are energy levels. So this one being a forbidden gap, it has a gap of about 3 electron volts. Electron volts is a unit of energy. So it has a forbidden gap of energy 3 electron volts. Now, when you increase the temperature of this insulator, it has no effect on the conductivity. If anything, it will now destroy if it's a piece of wood, it will just get destroyed and get burnt, but it will never conduct an electric current because we do not have any electrons in the conduction band. Then we have the semiconductors. For the semiconductors, we have the conduction band. At 0 Kelvin, it will be empty. At room temperature, it will be partially filled. For the valence band, it is again filled at 0 Kelvin. And of course, full, it will still be full at low temperatures. And the forbidden gap is smaller than the one for conductors. So that this one will have a narrower gap. This one is a narrower gap. When you increase the temperature, you can have that and heat energy being gained by the electrons, making them to move now from the valence band and cross the energy gap. You have given them enough energy to cross the energy gap, and they move to the conduction band. When an electron moves from the valence band and goes to the conduction band, it will create a hole in the valence band. So this electron has moved to the conduction band and has left a hole in the valence band. Now, the absence of an electron is called a hole, and it is considered to be positive. It's like the way you have a cell. One side is positive, a terminal, the other side is negative. And remember, the positive terminal does not necessarily mean that this body has positive charges in a cell. What it means is that you have a deficiency, the deficiency of electrons. When you have a deficiency of electrons, then you will talk about a positive terminal. When you have more electrons, you will have a negative terminal. Now, Ben, Washira, there's somebody who's raising up their hand. Can't remember who it was, a few seconds ago. Washira? I don't know that he's asking a question. Whoever it is, you can lower your hand and raise it again. I can't see anybody whose hand is up now. Looks like the person has lowered their hand. They are no longer asking the question. Okay. Okay, I can go on. I was talking about the absence of an electron being called a hole, and it is considered as a positive. Now, when the electron moves the valence band and goes to the conduction band, it means now this electron that has moved to the conduction band can now be used to conduct a current. At the same time, where we have a hole, another electron within the valence band will move from where it was and goes to occupy that hole, then creates another hole, then another electron moves to that hole. So within the valence band, we are having a hole movement just because one electron has moved. So you can imagine if many of them move to the conduction band, it means here we shall have a current due to electrons, and here we shall have a movement of holes, which we also call a hole current. The current is now here being considered as a result of hole movement. The hole has been created, an electron has moved. So we are still having an electric current, but this one is being propagated or being transmitted by the movement of holes. So here we have movement of holes in the valence band, and in the conduction band, we are having a movement of electrons. The electrical resistance will be reduced. Now we can have a current due to the flow of electrons and of course holes, meaning that when we increase the temperature, we lower the resistance in a semiconductor. Unlike for a conductor where when you increase the temperature, you increase the resistance. For a semiconductor, you increase the temperature, you reduce the resistance. Holes are very important as far as semiconductors are concerned. Up to that point, anyone with a question, if you have a question, please raise up your hand. 5 seconds. If I don't get any, I move on. Now, assuming we have all got the idea of the difference between conductors, insulators, and semiconductors in as far as valence bands are concerned, and also, I mean, the bands, the 3 types of bands are concerned, and also their conductivity. Now, moving on, when we have a pure semiconductor like the silicon I've talked about and the germanium, which are solely dependent on temperature, where if you want it to conduct, you increase the temperature, they are known as pure semiconductors. They have equal number of electrons and equal number of holes. Because if you look at this, we said if one electron moves up here, we'll create one hole. So then the electron moves from here to here, so we still have one hole. So 1 electron, 1 hole, 10 electrons, 10 holes. That is as far as a pure semiconductor is concerned. We have equal number of electrons and equal number of holes. Its conductivity is very low because look at low temperatures, they are insulators at that time. But when you raise the temperatures is when they start conducting. So you can imagine if you have to use a semiconductor in a radio where you have to heat it up for it to work. So we may not use semiconductors directly as an application, but there's something we do. In their pure state, they do not have any use. That is for silicon. You can see the lattice, the crystal lattice of silicon here. They are group 4 elements. You have done that in chemistry. They are group 4 elements. You may not classify them as conductors. You cannot classify them as insulators. That is why they are classified as semiconductors. They have 4 electrons on the outermost shell. That is why they will combine with 4 others to make a complete lattice. Now, for that intrinsic semiconductor, other than temperature, we want it so that we can use it at room temperature. So what we do, we add some quantities of impurities. That is, impurities in this case is not an impurity per se, it is an atom. You're combining it with another atom to increase its conductivity so that it starts conducting at low temperatures. So that we can have it used in our appliances or whatever. You may find its use even at low temperatures. Now that process of adding small quantities of impurities to an intrinsic semiconductor to enhance its conductivity is known as doping. So this one is to enhance its electrical properties, making it conduct better or increasing its conductivity. So all semiconductors in the use that we normally use are actually extrinsic semiconductors. So what is an extrinsic semiconductor? It is an intrinsic semiconductor that has been doped or that has impurities added to it to increase its conductivity. Kipchumba has a question. You have raised up your hand. Kipchumba, let me see where you are. Kipchumba Murkomen. Washira, can you see him? You unmute him. I can't seem to see him. Alternatively, you can put your questions on the chat. I'll still see it, other than having to keep checking where your names are. Oh, I have seen Kipchumba.
Mwalimu, I was asking.
Yes.
What can you what you have said about doping?
What I've said about doping?
Yeah.
I have said doping
Yes.
is the addition of impurities to an intrinsic semiconductor so that we can increase its conductivity. We are yet to see how that is done. Up to now, we just know we are adding an impurity, and this impurity, I said, is not an impurity per se, it's another atom you're adding to it so that it stops being an intrinsic semiconductor. We cannot call it now a pure semiconductor. You're adding something else to silicon, so it stops being silicon. It becomes something else. I hope I've answered you. Maybe when we look at how we dope, you will understand it better. Okay, moving forward. I cannot see any question on the chat. Now, how do we dope? We have two ways of doping it. Either we add a group 5 element to a group 4 element, and the group 5 element is known as a pentavalent. From the word pentagon, we know penta is 5. We add a group 5 element, which is called a pentavalent atom. For example, we can add phosphorus or we can add antimony. You add it to an intrinsic semiconductor, it will form, we'll see how it forms an N-type semiconductor. But you can either dope a semiconductor with a group 5 element, which is a pentavalent element, or you can dope it with a trivalent element, which is a group 3 element. And the group 3 elements examples, we have boron, we have aluminium, we have indium. Now remember, group 5 elements are the ones that are non-conductors, but group 3 elements are actually conductors. So how do we get the N-type semiconductor? This is why we are adding a pentavalent atom, a group 5 element. For example, phosphorus, to a group 4 semiconductor. Remember, all semiconductors are in group 4. So to a group 4 element or to a pure semiconductor, this is a silicon. Here you can see the diagram. We have phosphorus here and we have silicon. So this phosphorus, remember phosphorus has 5 electrons in the outermost shell. They will form covalent bonds with silicon. So we have this 1 electron combines with that, combines with this like that, so that eventually out of the 5, 4 have now formed covalent bond with silicon. But it means we shall have an extra electron because for phosphorus, they have 5 electrons in the outermost shell, while silicon has 4. And we are combining with 4 of them. So it means that we are going to have an extra electron somewhere because of the phosphorus. That extra electron will be a free electron, which will be used to enhance the conductivity of the silicon. So that now in this case, we are going to have holes from the original silicon. Silicon already had holes and had electrons. But now we are adding another free electron, meaning that we are going to have, if you use it in a circuit, you're going to have electrons as the majority charge carriers because you have added another electron, and then the holes are going to be minority charge carriers. Remember, the holes are said to be positive. So the holes will be minority while electrons will be majority because now you have added another free electron. You can imagine now a lattice with many of them. Here we have another phosphorus like that. So we are going to have many free electrons. So that now, in addition to what we had on the silicon, we are now adding another electron, or other electrons. That makes the electrons to be the majority charge carriers and the holes to be the minority charge carriers. What does that make phosphorus? Because it is donating an electron, we call phosphorus a donor atom. We call phosphorus a donor atom, so that now the silicon will have more electrons. Then we have a p-type semiconductor. This one is where we are doping silicon or a group 4 element, that is a semiconductor, with a trivalent atom. Trivalent is a group 3 atom, for example, boron, meaning that the outermost shell of boron has 3 electrons. Remember, for phosphorus, it had 5. This one has 3. And they are forming covalent bonds with silicon. You can see if it forms 3, I mean, there are 3 of them, and we are having 4 silicons. It means here we are having an absence of an electron. It needs an electron because boron has 3 instead of 4. So we are missing an electron. And that gap is called a hole. Just like I had talked about the holes when we're looking at the semiconductors. So there's an electron that we need an electron so that it can come and pair up. Unfortunately, there's no electron, and that creates a gap, and that is called a hole. So that now in a p-type semiconductor, the holes are the majority charge carriers. Remember, the silicon already had holes and electrons. So the holes now have increased because now we are having boron. So you can imagine many borons here, we shall have many holes. So the holes are the majority charge carriers and electrons are the minority charge carriers. These holes are such that if an electron now can move from here to here, so the holes are moving. It's like, normally I would use this example in a class. You just get somebody out of their sitting position in class, assuming we have the rows in the class, not the rows, the columns, whichever way, the rows going backward to the back of the class. The first person moves out. That desk becomes, or the chair becomes empty. Somebody from the next seat comes and occupies it. Then the person on the third row comes and occupies the second. The fourth comes and occupies the third, so that the gap is moving backwards, but the electrons are moving forward. So these holes are also having their own current. And that is why we say the holes are the majority charge carriers, while the electrons are the minority charge carriers in a p-type semiconductor. Now, because this boron is expecting to get an electron because of the creation of the hole, then we call it an acceptor atom, because it is supposed to accept an electron. So we call it an acceptor atom. Now, in all this, when you remove, you're having a hole, and if you look at the original part where I said in the intrinsic, this one, where when you increase the temperature of this semiconductor, then this hole, the electron moves to the conduction band, and a hole is created here. If it is an atom, I mean, since it is an atom, when you remove an electron, you create negative ions. When you remove not negative, we have positive ions. That is why we are talking about ions and fixed ions, minority and majority charge carrier. If you look at the p-type semiconductor, the holes I've said are the majority charge carriers, but as the hole moves away from the parent atom, now that is from the boron, then it means that the boron remains as a negative ion. And because it is not moving, then it is fixed within the crystal. We shall have what we call fixed ions. This one does not take part in the conduction. It is the electrons that are thermally generated that will be the, remember the electrons, in this case for a p-type, the electrons can only be thermally generated. They can only come in when you hit that semiconductor, while the holes are coming as a result of doping. Then for the n-type, we have the parent atom, that is a phosphorus. Now that it is an electron is moving away from the parent, then makes it a positive ion. Then the holes will be this, the phosphorus becomes a positive fixed ion. The holes are thermally generated. Electrons are the majority charge carriers. So in this case, we have fixed ions, we have majority charge carriers, and we have minority charge carriers. Now there's somebody who calls themselves Code. Me, I don't know who that is. And I cannot see him. I may raise up his hand.
Kindly remove the live transcript.
The
live transcript.
Which live transcript? Please advise, I can't understand what you say.
Those like subtitles.
Well, you know, I have maximized it. Allow me to. Okay, which one? I should log in with my phone so that I can see what you're seeing, because I can't see what you guys are saying. The problem with the phone, if I put it on, it will start making a lot of noise. But even if it does, allow me to. You'll just hear noise kidogo. At least I just have a clue about what you're talking about.
Madam Tabitha, can you hear me?
Yes, I can hear you, Ashira.
Just continue. I have just disabled the transcript. It's not.
Oh, it was
okay.
It was saying what I was reading.
Yeah. What you are saying, it translates.
Okay. I've understood now what he's talking about. Sorry, I didn't know it was on. I didn't know it was on.
Okay.
Okay, so I can continue, Cindy?
Yeah, just continue.
Okay, I don't even have to log in with my phone then. Okay, anybody with a question? If there's none, then we can continue. We've talked about the fixed ions. We've talked about majority and minority charge carriers. For the p-type, remember the holes are the majority charge carriers, while the electrons that are thermally generated are the minority charge carriers. Then we have the fixed ions. They don't participate in the conduction. For an n-type, the electrons are the majority charge carriers, while the holes, which are thermally generated, are the minority charge carriers. Now, what would happen if you put a p-type and an n-type semiconductor together? On one side you have n-type, another side you have p-type. You bring them together. Remember, they don't work on their own. You have to, normally we would put a junction. So one part we have a p-type, another side we have an n-type, and that forms what we call a p-n junction diode. So this is where you have doped one side p-type, an intrinsic semiconductor p-type, and on the other side, you have doped it now to become an n-type. The p-type, of course, you have used a trivalent atom. The n-type, you have used a pentavalent atom. So one half becomes a p-type, the other half is an n-type. So you had one big semiconductor. One side you doped p-type, the other side you doped it to make an n-type. Here in the n-type, we have electrons as the majority charge carriers and holes as the minority. On the p-type, we have holes as the majority charge carriers, while electrons are the minority charge carriers. So what will happen at the middle part? You'll find that this ones, the holes on this side will start moving. The electrons will start moving to the side of the holes, and the holes on the p-type will start moving to the n-type up to a particular point. So there'll be movement at the junction where the electrons are diffusing to the holes and the holes are diffusing to the other side, the holes are diffusing to the electrons. Now you're going to recombine the charge so that it becomes a neutral position. A region of about 10 to the power of -4. This should have been a subscript, a superscript. I forgot to put that as a superscript. 10 to the power of -4 to 10 to the power of -6 meters. A very small region. A region of uncovered fixed ions will be formed on the other side of the junction. So we call this part, it sets up what we call a potential barrier. Remember, let me go back to this. We have electrons have moved from the n-type. They have, these ones at the center, maybe up to this point, and another one up to maybe this point. You find these ones that are near the center, the electrons have moved from the n-type, they have gone to the side of the holes. The holes have moved this way. So at the middle part, we have ions that are not, they have no electrons, they have no holes. That is why we are talking about that are uncovered, the region of uncovered fixed ions. They have no electrons, they have no holes, so it's just a fixed ion. It creates what we call a potential difference, which is known as a potential barrier. it sets up a potential difference known as a potential barrier, which will make the electrons now not move from, just a minute, minimize this, just a minute. It should have been a continuous sentence. We have the intense sets up a field that will stop further diffusion of mobile charges. Now you're creating a potential barrier, meaning that for the electrons to move now from the N-type to go to the P-type, they would have to overcome the potential barrier. And for the holes to move from the P-type to the N-type, they have to overcome the potential barrier. That layer, that region of uncovered fixed ions is known as a depletion layer. Looking at it from a diagram, you can now see these electrons have now been neutralized to the positive. So here we have nothing. We only have fixed ions. Fixed ions that are uncovered. This side we shall have electrons as the majority and holes as minority. Here we have holes as majority, electrons as minority, and a depletion layer in between. Now for these electrons to move from the P-type to the N-type, lazima ipite the potential. There has to be you have to give it some boost from one side. We shall see how that is done for it to overcome the depletion layer. I hope the depletion layer is now clear. If you're following what I'm saying, you can raise your hand or put a reaction. Because now I'm going to the next thing. Remember when we were starting, I gave you looking at the objectives of the topic. The first one was difference between conductor and insulators. That one is a tick. We have already covered that. It's a very short chapter, by the way. Intrinsic and extrinsic semiconductors, we have covered that. We have also done doping of a semiconductor. We have done that. Now we are at the working of a PN junction diode. We are halfway through the topic. So that is why I'm giving you a chance in case you have a question, or if you are happy with, or you're following what I'm saying, you can just put a reaction. Raise your hand or put a reaction, of course, a positive reaction on or you just chat and say you're following so that I'm not talking to myself or I'm not teaching. Okay, please explain again how the potential barrier is formed. Now I said, when you have a junction diode, this is where you dope. You have an intrinsic semiconductor. You dope one half of the semiconductor with a trivalent atom, making this side a P-type. On the other side, you dope it with a pentavalent atom and make it an N-type. So one side we have a P-type, the other side we have an N-type. The moment that is done, you find the holes on the P-type at the middle part, hapo katikati where the junction is. The holes on the P-type will start moving now to the side where we have electrons, because the holes and the electrons, once they combine, it becomes neutral. Now we don't have anything like holes and electrons again, because the electron will now occupy the hole. Then the electrons on the side of the N-type will now move to the P-type. Now that can only happen up to a certain point, because here we will now have fixed ions. There are no electrons. Remember this diagram, this should have been blank. We have, maybe I can, just allow me to check something, whether on my notes, I may be having a better diagram. Just give me a minute. Those who are in for North, I mean, that is for Dayton, and for Q, that is, I mean, for North, Dartmouth and Dayton, they have these notes. Even in the diagram, I think it's the same. Anyway, just know that at the middle, here we have fixed ions. we no longer have electrons and we no longer have holes because they have already recombined the holes and the electrons. These electrons have now gone to occupy the holes. So now we no longer have free electrons. We don't have holes. Now this depletion layer forms what we call a potential barrier because we are having just uncovered fixed ion. Ni kama pameachwa, like, what would I put it? How would I put it? You'd have to give these electrons on this side enough energy to move from the n-type. They pass, in kama mlima, there's some barrier that has been created, like a resistance has been created, so that now they are not able to move from the n-type to go to the holes, to the p-type, and the holes on the p-type are not able to go to the other side. Because here now we no longer have anything. It's actually a potential barrier, like a potential difference. These ones will have to be given energy to move beyond these fixed ions to go to this side. And the n-type, the electrons will have to be given enough energy to move from the n-type and pass this depletion layer. Actually, it's like a resistance of some sort. That's why we are calling it a potential difference. I hope whoever asked the question has understood. So the depletion layer is an insulator? No, it's a potential barrier. We cannot call it an insulator. We'll call it a potential barrier. Why? Because if we connect this circuit to an external circuit, maybe to a cell, which we normally do, that's the next part I'm going to teach, that is biasing, where now you connect the p-type to a cell and the n-type to a cell, it can now get energy. The electrons can now get energy to move from the n-type and go to the p-type. Or the other way around, the holes can now go to the other side. They will have enough energy. So we cannot call it an insulator. We can only call it, somebody saying they cannot see my screen. Are there people who are seeing my screen? Why use silicon for both n-type and p-type? Because you cannot, the intrinsic semiconductor you're using is one. You can use germanium. It's only that for purposes of teaching, we just use silicon, but you can also use germanium as an intrinsic semiconductor. But you cannot put now germanium and silicon together, because what are you making? It's like putting copper and aluminum together. You're not having, it doesn't make any sense. So you can either use a germanium intrinsic or silicon, but for purposes of teaching, we normally would use silicon. But even if you wrote germanium, there's nothing wrong. All we need is an intrinsic semiconductor. Please explain the difference between p-type. Allow me to go back a bit to these questions. Holes. I think the one who asked about the holes by now, Amejua. Where we don't have an electron, an absence of an electron is called a hole. P-type and n-type. N-type we dope with a pentavalent, where we have an extra electrons. P-type we have holes, that is an absence of an electron because of the boron, 3 electrons on the outermost shell. So we need 4, but now we are having 3. So we have an absence of an electron, which is a hole. That makes it a p-type semiconductor. We can see the screen. So the one who cannot see the screen, probably it's your network, the connection that is getting low. Does the potential barrier contain any charges? No, it does not. So the depletion layer prevents both holes and electrons from passing through. Yes, unless now you give it an external, get a source of energy to move now from the other side. What about germanium and I'm not seeing the difference. I'm seeing germanium and I'm seeing germanium. I don't know what that person is asking. Jeff, I don't understand your question. Please repeat about intrinsic and extrinsic. Now, intrinsic, I said, intrinsic are those, let me go back to the screen. Intrinsic are those that will depend solely on temperature. Remember we said that when you increase the temperature of a semiconductor, the electron here will get enough energy now to move from the valence band to the conduction band. And this is solely dependent on temperature. And when it is solely dependent on temperature, we call that an intrinsic semiconductor. It's actually a pure semiconductor. But the moment, because you cannot keep heating semiconductors for us to use, like you can imagine if you have to use it in a radio, that's why you heat up the radio for it to work. So we don't do that. We now dope it so that we are going to have, other than thermally generating them, we are still thermally generating them. If the temperatures increase, they'll still be there. But now here, we are now getting an extra source of electrons or an extra source of holes. And that gives us an increasing conductivity. So that, sorry, so that other than the thermally generated electrons and the thermally generated holes, we are having another source of electrons or holes. And that is what creates, that is how we end up having extrinsic semiconductors. Sorry, I've been unwell. Allow me to put a video kidogo, still on electronics, as I recover a bit. And even it will explain for you maybe better about stop the share. I can see your questions. Allow me to answer them after I've recovered after some minutes. I'm trying to get the videos. I think I had saved them here. Once you understand the formation of the holes, it becomes very easy to follow up. Like this, escape. Nice this one. I had saved some videos on don't seem to be on that class. Let me just continue. I think I think I'm better. Not as bad. Okay, back to the questions. Somebody's saying they cannot understand about the uncovered fixed ions. That is what happens when we have. Let me share my screen again. When you bring a fixed, an N-type and a P-type, I said the electrons will move from one side, from the P-type, the holes will move from the P-type to the N-type, and the electrons will move from the N-type to the P-type, creating a point where we have no electrons, we have no holes. And that is what I talked about, a potential barrier, which is a depletion layer, which is there where we have uncovered fixed ions. They are, okay, you don't even have to say uncovered. They are fixed ions, but now without holes and electrons. That is why we call it uncovered. Let me go to, is the crossing of electrons to the conduction band continuous? That is, if as long as they are thermally generated, yes, they will continue moving from the valence band to the conduction band. That's why we said that those holes will now carry a current as long as that is happening. But then when you're having an extrinsic semiconductor, the current will flow as long as you have now connected it to an external circuit. Maybe when I do biasing, you'll understand. You know that somebody's asking what a diode is. We are coming to the diode. Now, on its own, the way it is right now, you cannot use it. You just have created a PN junction without, on one side you have doped P, the other side you have doped N, and you have a depletion layer. Now you cannot use it. You have to connect it to an external circuit for it to work. Now that brings us to what we call the biasing of the PN junction. This is the PN junction. Now biasing means connecting it to another external potential difference, like you connect it to a cell or a battery. If you connect the P-type to the positive and N-type to the negative, we call that forward biasing. Why is it forward biasing? Because the P-type is where we had holes. The N-type, we had the majority electrons as a majority charge carriers. In between, we had a depletion layer. The external circuit, we expect this side to have a deficiency of electrons. This side to have electrons. These electrons on the negative terminal will push these electrons on the side where we have the N, and they pass the depletion layer and they go to the P-type. And as they do that, we are going to have a current flowing, because now we have overcome that depletion layer that had been created. You have now given it from an external, we have now a external potential difference you have applied. And this being electrons, they now come, they will repel the electrons on this side, and they push them so that now they pass through the depletion layer, go to occupy the holes, and on the other side, this is potential difference, this is positive. It will push these holes because they're having the same potential. It will push these holes to come and close in with the electrons, and we have a current now flowing from positive to negative. Though the electrons are now moving from negative terminal to the positive terminal. Remember, current flow is a flow of electrons. As I said, the conventional direction of a current is positive to negative. But essentially, the electrons move from the negative, where we have a high potential of electrons, to the positive. But because they had already, the scientists had already said that the current flows from positive to negative, that's why we say the conventional direction is positive to negative, but the flow of current electrons is from negative to positive. So these electrons will move from here, where we have a higher potential of electrons, or where we have more electrons. They will push the electrons that are here, repelling them. And when they repel, these electrons are repelled towards where we have holes. And now you have overcome the potential barrier that had been created. And that makes an electron current to flow, or we have a current flowing. That is why we call it forward biasing. Now, here we are, we have the P-type. Here we had holes as a majority charge carriers. You can see the holes are many. Here we had electrons as a majority charge carriers. You have connected the P-type to the positive, that is the anode. You have connected the N-type to the negative, which is the cathode. So you're going to overcome this depletion layer that had been created once you had the P-type and N-type put together. So the electrons will move from the negative terminal like that. It repel the negative, the electrons, they will move beyond the depletion layer. And these ones that are, this is the P side, will push the holes this way, and now they'll recombine, and we have a current that will be flowing now from positive to negative. That is forward biasing, where you narrow the depletion layer and you reduce the resistance, and now the holes can now flow to the N side, and the electrons can now go to the P side. That is the majority charge carriers. They're the ones which are crossing the junction. So a current will conduct, and if you put a bulb, now you'll be able to, the bulb will light. And now what we have created is called a diode. Somebody was asking me about a diode. We have now a diode. Once that the PN junction is actually called a diode. It's only that we don't say a PN junction diode, but that is a diode, a PN junction diode. And we can either forward bias it. Remember, a diode will only conduct a current in one direction. If you forward bias it, it conducts a current. If you reverse bias it, which is what we are going to look at, it will not conduct a current. Now the applied voltage, which is the one you're creating here, we are calling it VE, is greater than the internal potential barrier. That greater than that, the potential barrier I'm talking about is the depletion layer. It will be greater than the depletion layer, posing the latter by repelling the holes from the p-type and electrons from the, this is just what I have said, reducing the potential barrier and therefore connecting, the current will flow. In the reverse bias, here we shall now connect that junction diode in such a way that now the P will be negative, connected to the negative, and the N to the positive. Now, I want somebody to tell me what you think will happen. Let me go back to this screen. This time it will be the negative. The P-type is connected to the negative, and the negative is connected to, the N-type is connected to the positive. Can somebody tell us what you think will happen? I've already explained the other side. Somebody's asking about the N-type. N-type, you form it by doping an intrinsic semiconductor with a pentavalent atom. And like phosphorus, pentavalent has 5 electrons on the outermost shell. You'll have an extra electron. Now, Mwenda, let me ask you to unmute, then you'll give us the answer. When we reverse bias,
Current will not flow.
How? What do you think will happen? You have not explained fully. Using this diagram, please explain.
So you have connected the positive terminal to the cathode and the negative terminal to the anode.
Which is a positive terminal to the cathode? I thought positive terminal is a cathode. Maybe I would, supposing I gave you this first diagram, look at the first diagram, now you're doing it the opposite. You can now see my diagram, the 100 forward bias.
Yes.
You're connecting, this time you're doing the other way around. The P is connected to negative, and the N is connected to positive. So explain, and remember there's a depletion layer. Or better still, I can use that.
So
P to negative, N to positive.
in the N side, the side of N.
The N type.
The positive charges from the positive terminal will attract the electrons at the N type. So there at the beginning of the N type there will be attraction, and also in the P type, in the side of the P type, the electrons that will have accumulated there will attract the holes in the P type. So the depletion layer will increase. So the potential barrier is becoming bigger. So now